Welcome back to Statistical Methods. This is week 13, lecture 1, where I will be covering chi-square tests of goodness of fit. Now with Z and T tests in ANOVA, we can handle a wide range of research questions involving numeric equal interval dependent variables. What happens when my key dependent variable is categorical in nature? So for example, if I asked everyone in here whether they preferred chocolate, vanilla, or strawberry ice cream, scores would now be which flavor a person preferred. I would end up with a table of frequencies for each flavor category. So for example, the number of people preferring chocolate, the number of people preferring vanilla, and the number of people preferring strawberry. Now these numbers do not reflect sample means, but rather the number of people responding with each flavor. So frequencies within each category. 20 people liking chocolate, 23 vanilla, and 12 for strawberry. What kinds of research questions can I ask here? Perhaps whether people seem to prefer one category over another. In other words, whether frequency counts look similar across the cells, with 1/3 of people preferring each flavor, or if observed frequencies differ from this pattern. Another way to put this is that we want to test whether our set of observed frequencies differs from some set of expected frequencies. This expected set of frequencies represents our null hypothesis in this case, and usually reflects chance. So that is, all categories have equal frequencies. However, we can test our observed frequencies against any specific set of expected frequencies we want. Chance, or equal proportions across categories, won't always be the most sensible null hypothesis. For example, what if I wanted to test the current racial makeup of the United States population, and whether it's different now from what it was 10 years ago? It wouldn't make sense to test my current observed frequencies against chance. Rather, I would want to set my expected frequencies to whatever they were 10 years ago. Thus, I need a hypothesis test that will allow me to test whether my observed frequencies differ from my expected frequencies to a highly improbable degree, assuming the null hypothesis, or that the true frequency breakdown in the population indeed looks like the expected frequencies. Sounds like typical null hypothesis significance testing logic, but what test statistic/comparison distribution will we use? Is there any way to calculate sample means here? Or sample variances? What about a correlation coefficient? Well, none of these approaches that we've learned will allow us to answer such a research question, because they all begin with the assumption that our dependent variable is a numeric equal interval variable, from which we can talk about things like means and variances. Rather, we'll need a new kind of statistic that quantifies the degree of mismatch between our observed and expected frequencies. This statistic is known as the chi-square, or represented by this symbol here. This type of test we're describing, in which we test the deviation of observed from expected frequencies for a single categorical variable, is known as a chi-square test of goodness of fit. The idea is that we're testing the degree of fit, or matching, between observed and expected frequencies. Also different from what we've done before, in that we don't have a clear independent or predictor variable that's doing the explaining here. The goal here is simply to describe frequencies and their mismatch from expectations, as opposed to test some specific causal influence of an independent variable. So for example, in our ice cream example, all we can conclude is that more people like one flavor than the other. We can only make a guess as to why this is the case. This is true of goodness of fit tests, but not all chi-square tests. We'll learn of another type of chi-square test next class that will allow us to actually detect dependency on a second categorical variable. Now let's see how this works in another sample involving categorical dependent variable with just two possible response options. In this case, our expected null set of frequencies will not reflect chance, but rather a specific pre-existing set of expectations. So, a researcher wants to know the breakdown of religious beliefs, so religious versus non-religious, of US physicians. They collect a representative sample of 1,000 doctors from the US and ask them whether or not they adhere to specific religion. Thus, two possible values: religious and non-religious. And let's say that I expected, based on prior census data, that my sample of doctors would end up being 90% religious and 10% non-religious. Or in other words, 900 religious doctors and 100 non-religious doctors. But the data I actually collected say that there were 76.5% religious doctors, while the other 23.5% of doctors said that they do not adhere to a specific religion. Now, the question I want to test here is, do these observed values differ from the expected values enough to say that the religious composition of the doctors has changed since the last census? In null hypothesis significance testing terms, is the observed expected deviation highly improbable, assuming the null, or the expected frequency breakdown, from the prior census? Now, we'll need the actual statistic that reflects the degree of mismatch. For each individual category, so for example, first religious, then non-religious, take the observed frequency minus the expected frequency, and since we're interested in both positive and negative mismatch, square these differences, and then weight these squared differences by dividing by the expected frequency. For example, is the frequency out of 10, out of 100, out of 1 million? And then do this for each category, and then sum the categories mismatch. So you're calculating this for religious and non-religious, and then adding them together. And the final number we obtain is the chi-square statistic. And it quantifies the overall amount of mismatch between your observed frequencies and the expected frequencies. So in our example, remember that my expected frequencies for a sample of 1,000 doctors were 900 religious, 100 non-religious, and my observed frequencies were 765 religious and 235 non-religious. Thus, this graph here, this table here. Now, to calculate religious mismatch, you take your observed 765 religious minus 900 expected religious, square that, and divide by 900, which equals 20.25. And for non-religious mismatch, take your observed value, 235, minus your expected value, 100, square it, and divide by expected, 100, which equals 182.25. And then you sum these two together to get your chi-squared test statistic. So 20.25 plus 182.25 equals 202.5. Now imagine that the observed frequencies in this example were as they appear below instead of what I just described. Now I'd like you to calculate the chi-square on your own. So pause the video here and calculate the chi-square. Now we'll need to figure out whether the chi-square we calculated is sufficiently improbable, if the null is true, to reject that null hypothesis. To do so, we'll need to know the probabilities of attaining various chi-square values when the null is true. In other words, what the null probability distribution of chi-squares looks like. Fortunately, the chi-square distribution is another probability distribution with known properties, just like the t, f, and z distributions. As the chi-square can only take on positive values like f values, its distribution is right-skewed. Its precise shape depends upon its degrees of freedom, just like with t and f distributions. And for a chi-square goodness of fit test, the degrees of freedom equals the number of categories minus 1. So religious and non-religious, 2 minus 1 equals 1. This is how the shape changes as a function of degrees of freedom. And as previously, we determine the cutoff value for a chi-square by using either a chi-square table, which can be found in the textbook, or using the Shiny app. I prefer the Shiny app, which can be found at the link here. You can adjust the probability to 0.05, our cutoff, enter your degrees of freedom, in this case it's 1, and you get the chi-square cutoff. So chi-squares obtained greater than this are significant, and those lower than this are non-significant. Equal to this is significant as well. Actually, you want this to be higher, since your p-value has to be less than 0.05. Now, in our example, we had two categories, religious and non-religious. Our cutoff value, using a degrees of freedom of 1 and a significance value of 0.05, is 3.84. So in our first hypothetical table of results, the chi-square was 202.5, and here you can clearly reject the null. 202.5 is much larger than 3.84. But in our second hypothetical table of results, our chi-squared obtained was 2.5, in which we'd fail to reject the null, since this is smaller than our cutoff of 3.84. Now, in the first case, we would conclude that our observed frequencies are actually different than the expected frequencies based on the prior census. Our level of mismatch, as quantified by a chi-square, is sufficiently improbable, assuming the null, to conclude that there is such a difference. In the second case, however, we see that our numbers match the previous census quite well. Accordingly, we find a small chi-squared that is non-significant, and thus fail to reject the null, that our observed and expected frequencies match.